So here's a problem. We have a mixture having a molar analysis of 80% nitrogen and 20% carbon dioxide. It enters an insulated compressor operating at steady state. It enters at 1 bar and 300 Kelvin and a given mass flow rate of 4 kilograms per second. And it is compressed to an exit pressure of 3 bar, so it goes from 1 bar to 3 bar, and then they give you the exit temperature of 440 Kelvin. The dead state or the environmental temperature is 300 Kelvin. Neglecting kinetic and potential energy effects determine first part A, magnitude of the power required, part B, rate of exergy destruction, and part C, the isentropic compressor efficiency. All right, that's a lot to digest. What I'm going to do is I'm going to continue to use other pages because I can't fit it all on one page. But I'd like you to set up an illustration of the compressor, inlet stream 1, exit 2, and then just tabulate the information. Oh, the temperature at 1 is known. That's 300 Kelvin. And the temperature exit is given to be 440 Kelvin. The pressure 1 is 1 bar. And the pressure 2 is 3 bar. They say it's well insulated, so we'll put something like that indicating no heat transfer from the boundary to the surroundings. And we want to calculate the power required to run it, to drive the compressor. So I'm going to put it going in and W dot into the compressor. So we'll deviate from our sign convention, the traditional sign convention, for a control volume that encloses the compressor. So the first question is, how do I determine the magnitude of the power required? What am I trying to solve for? W dot C. So I do a first law analysis for that system. There's a Q dot equal to 0, changes the kinetic potential energy equal to 0 at steady state. I've done this so many times. I can either write it on a mass basis. Let me do it this way. Mass flow rate times the change in the enthalpy. And I pause for a minute because I put the arrow going in and the exit enthalpy is going to be high. That's right. That's correct direction, everything. Now, because I have multiple components, I want to do a summation over all of the components. And so the mass flow rate of every component and then the change in enthalpy of that component. You could also say, well, I'd like to write it a different way. I'd like to write it the sum of n dots. What? N dots? I'm familiar with mass flow rates. But you could also do it on a molar flow rate basis. And then you would have the H2 minus H1, but this time put a bar on top of those for each of those components. What do you mean by bar? Well, that's enthalpy. What would be the SI units for this H bar? Isn't that kilojoules per kilomole? And if you use the tables, guess what? The gas tables, the ideal gas tables, where you have CO, CO2, N2, H2O vapor, oxygen, they're going to be on a molar basis. So either one of these work. Because how do I move back and forth? Let's ask a clicker question. Somebody says, I'm given H bar, or I can look it up, right? Maybe I should have emphasized that. These H bars, this is at the temperature T1, which is 300 Kelvin, and this one's at a temperature T2 of 440 Kelvin. For an ideal gas model, there's 3 things that we remember. We remember PV is equal to RT, the ideal gas equation. U is a function of temperature only, and H is a function of temperature only. And so we're going to use it. Hey, H, I don't need, it's a function of temperature only. It's not a function of temperature and pressure. So all I need is know that T1 and I get H1, and I know T2 and I get H2. So, but the thing is, I get H bar out of the appendix. Let's say I get H bar 1, and I really want to calculate H1. So the question is, I think I'm going to either multiply by the molar mass or just ignore it and just equate them, or divide by the molar mass. Which one is correct? A, B, or C? What is big M again? Molar mass. So let's do this. Remind me, what are the SI units for H without a bar? Kilojoules per kilogram, true? All right. Remind me, what are the SI units for H bar? H bar has something like kilojoules per kilomole. That's what we just wrote up here. All right. What are the SI units of cap M? Kilograms per kilomole, or the reciprocal? That one, kilograms per kilomole. So I re-asked the question. Which one's correct? All right, so if I multiply by kilograms per kilomole, don't the kilograms cancel? I mean, the kilomoles cancel, and I'm left with kilojoules per kilogram. I mean, it improved, but I was hoping that it would get close to 100%. But I got 8 people, 1 guessing or I don't know, and then 7 elsewhere. So anyway, there you go. All right. So I was able to shift the class a little bit, but not much. So I need to get either the molar flow rates or the mass flow rates. And I know how to get these out of the tables, right? And so let me do this. I'm going to introduce a new page. And I'm going to just say, look, I'm going to have a species, the nitrogen. And what is the molar mass for nitrogen in kilograms per kilomole? Kilograms per kilomole. Maybe I should tuck that down a little further. Nitrogen. I had looked that up in a table. 28.01. Then I'll look it up for carbon dioxide, 44.01. What was my given mole fraction? It was 0.8 and 0.2. At this point, you can calculate or do the yi times mi. And then when you sum that actually give you the mixture molar mass. So 0.8 times 28.01. I don't remember what that is, but 0.8 times 28.01, and then 0.2 times 44.01, and then you sum that up and you get 31.21. So the mixture molar mass is 31.21. And then you calculate the mass fractions. What's the mass fraction? Well, it's the YIMI divided by the mixture molar mass. Right? So this one comes in at about 0.718, and this one comes in at 0.282. So even though it's 80% by molar fraction is 80%, its mass fraction is lower than 80 because it's not as heavy of a molecule. It has a lower molar mass than the carbon dioxide. Okay. Now, you can sit there and think, well, if I had a mass flow rate of 4 kilograms per second, could you tell me what the mass flow rate in kilograms per second is for each of those species, for the nitrogen? You could. Wouldn't that be 4 times 0.718? Sure. And then the other one would be 4 times 0.282. Okay, so you could calculate those as numbers. I don't know. I have them on my sheet of paper, but it'd take me a minute to find them. Likewise, you could say, can I calculate the molar flow rate in kilomoles per second? Sure. If you had the mass flow rate calculated, here, that's a good question, clicker question. I want to calculate the molar flow rate. Somebody says take the mass flow rate and just they're equal. No, somebody says take the mass flow rate and divide by the molar mass, or take the mass flow rate and multiply by the molar mass. One of these is correct. Answer A, B, or C. And let's do this. What are the SI units for M dot? M dot SI units are kilogram per second. All right. So if I put kilogram per kilomole like this, what do I get? Kilomole per second. So didn't I divide by the molar mass? So one student's torturing me today. So didn't I do that? Correct? Good. Okay. So you can calculate that molar flow rate. So little table, little bit of work, I can get the mass flow rate, molar flow rate, whatever I like. So when I come back here, I want to maybe use this form or this form. Either way works. Okay? If I go back here, I calculate a molar flow rate for the nitrogen of 0.1025 kilomoles per second. And for the carbon dioxide, 0.0256. I should have had more digits. And likewise for the mass flow rate, the mass flow rate is that's the mass fraction, 2.8719 kilograms per second, and the mass flow rate of 1.1281 kilograms per second.
How did you get the mass fractions again?
This 0.718 is the mass fraction of the nitrogen. It'll be the mass of the nitrogen divided by the total mass, which is the mass of the nitrogen plus the mass of the carbon dioxide, which is the 0.8 times 28.01 divided by the 31.21. Yeah.
Okay.
So I'm going to insert a new page, and so we calculate W dot equal to, I'm just going to leave it like the molar flow rate of the nitrogen times H bar at 2 of the nitrogen minus H bar 1 of the nitrogen plus the molar flow rate of the carbon dioxide, H bar 2 minus H bar 1 of the carbon dioxide. Now, so who has an appendix? Can you look up and see what is H bar 1, which would be for the nitrogen? I think this one is 8,723 kilojoules per kilomole for the nitrogen. And this one is 12,811. And then likewise for the carbon dioxide, 15,054 minus 9,431. Again, those are out of the appendix at those two temperatures. The one, T1 is 300 Kelvin, and T2 is 440 Kelvin. They look okay? Good? All right. So in the interest of time, basically we get the answer 563 kilowatts for the power. All right. Now, for part B, what is the rate of exergy destruction? How am I going to calculate the rate of exergy destruction within that compressor? That's right. I'm going to race down here to make a little room. And what we recall is that the exergy destruction is proportional to entropy generation. This textbook uses sigma dot for rate of entropy production. We multiply that by our given dead state temperature of 300 Kelvin, and boom, we have exergy destruction. Okay, how am I going to calculate sigma dot now?
You don't have to multiply by mass flow?
Well, this is a dot and that's a dot. So just like we had W dot up here. So how am I going to calculate the sigma dot? Second law for the control volume around the compressor. And it'll look a lot like the first law, but it's the second law. Okay. Do we have any transfer of entropy with heat transfer across the boundary of the control volume? No, because it's a well-insulated compressor. So you just have mass flow carrying with it entropy. And so you pick up that it's the mass flow rate times the exit S2 minus S1. And you say, well, we have a mixture, so we sum over the mass flow rate for each component and then change in entropy for each component. Somebody says, I prefer to work on a molar flow rate basis, so wouldn't that be the sum over n dot I times S bar 2 minus S bar 1 for I over all the I's. And there's only two I's, nitrogen and carbon dioxide. Do you see the parallelism between this is not plus, this is equal, between the first law and the second law? Makes sense? So we already had solved for the molar flow rates. Let's work in the molar flow rate, or let's work over here with the S bars. So I'm going to switch to another page and expand that, insert new page. And so we're going to have S2 minus S1, bar. How am I going to calculate that? Just like we had the H2 bar minus H1 bar, that was a question, how do we get that information for the first law? Same way for the second law. So this is equal to S2 bar naught minus S1 bar naught minus R bar, natural log P2 over P1. That look okay? Look familiar? Where do we get these? From the same table where we got the H bars. Yeah, it's the same gas table. Hey, I don't understand what this naught is. Let's just throw it out. It's meaningless. S with a naught or without a naught, it doesn't matter. Just like S with a bar, without a bar, it doesn't matter. No. It means something. It means low pressure. And so the pressure effects are incorporated in this term on the change in the entropy. All right? Okay. Now, let's do this. So let's write it out that sigma dot is equal to the molar flow rate of the nitrogen times S bar naught 2 of the nitrogen, S bar naught 1 of the nitrogen minus R bar. And let's think about these pressures. P2 of the nitrogen divided by P1 of the nitrogen, right? So, I mean, I could put these in brackets, etc. Now, that P2 of the nitrogen is the outlet pressure times the mole fraction of the nitrogen in the outlet stream. So and when we look at the compressor, did the mole fraction of the nitrogen change from inlet to outlet? No, it stayed 80%. What changed? The total pressure. So when we look at this ratio of pressures is like the mole fraction of the nitrogen times the total pressure at the exit, the mole fraction of the nitrogen times the total pressure on the inlet. The mole fractions don't change. You're going to be left with the natural log of 3. 3 bar divided by 1 bar, natural log of 3. A little bit of logic there, but I think we can handle it. We have the minus R bar. Let's do this. We said that this one was evaluated at a temperature of 300 Kelvin. What value do you get out of the table? Do you pick up 191.682? Very good, thank you. And then this one's at a temperature of 440. 202. Now I think I wrote that number down wrong. 202 point what? 863. Thank you. Okay. And then there's a minus sign in between. So there you go. There you go. Now you carry over the molar flow rate, and then you do the same thing. The molar flow rate of the carbon dioxide, N dot of the carbon dioxide. Then you have S bar naught of the carbon dioxide at state 2, S bar naught state 1 minus R bar natural log. I'm just going to put 3 there. Same thing. Same logic. And then when we find this is 229.23, and this one's 213.915. Hey, I forgot what is R bar. 8.314. Is it the same over here and over there? Sure is. Yeah. Okay, so you can calculate the rate of entropy generation. I think it comes out to be 0.3683. Hey, what are the SI units on this? Clicker question. I think the SI units on this are going to be kilowatts, answer A. Kilowatt times Kelvin, answer B. Kilowatt times kilogram per Kelvin, answer C. Kilowatt per Kelvin, answer D. And kilowatt per kilogram Kelvin, answer E. What are the SI units for this sigma dot? All right, so this is probably just one of those recalls. It's kilowatt per Kelvin. Kilowatt per Kelvin. Now, so let me get rid of all this garbage. Kilowatt per Kelvin. Kilowatt per Kelvin. Somebody said, we were asked to calculate the rate of Exergy destruction. The rate of Exergy destruction. Hey, what are the SI units of the rate of Exergy? Not a clicker question, just kilowatt. You're going to multiply temperature in Kelvin times kilowatt per Kelvin. The Kelvins cancel, you're left with kilowatts. And we come in with the rate of Exergy destruction. There it is, 111 kilowatts. All right, part C, isentropic compressor efficiency. Okay, how do you calculate the isentropic compressor efficiency? Isn't that the symbol for it? And isn't it the ratio of some W dots divided by W dots, where the minimum, it can't be over 100%. The maximum would be 100%. And so I always have to think, do I put it as if it's reversible that way, or do I put it with the reversible down, the numerator gets the reversible and the denominator gets the actual? That should be an iClicker. I don't have space for the iClicker. So there you go. So isn't that the definition? So the question is if I could just get two numbers and take their ratio, I would have the answer they're looking for. Okay, have we already calculated one of those two? Yeah, and from part A, didn't we just calculate this from part A? That's great. See, we're almost there. So how do I calculate that W dot S? I know what that subscript S means. It means it's isentropic compression, right? So what's the strategy there? Well, you say, go back to this equation. W dot is going to be the molar flow rate times H bar 2 minus H bar 1 plus the molar flow rate times the H bar 2 minus the H bar 1. This is all for the carbon dioxide. This is all for the nitrogen, right? Okay, now somebody says I need to do that if it's isentropic. So it's reversible, adiabatic. That's how the compressor is behaving, hence it's going to be isentropically compressed. It doesn't change H bar 1, it changes H bar 2, doesn't it? And it doesn't change the molar flow rates. And if you think about it, these were only a function of temperature. It really is, I need to get T2S. Hey, T2 actual was 440. But what is T2S? Oh man, this is a terrible problem. Well, what do we do? So that it's like you need to find T2S. How are you going to find T2S? Because if I had it, I'd get the H2 bars and I'd be done. go back to part B, and you said, hey, we had this equation, sigma dots equal to the molar flow rate times nitrogen plus the molar flow rate. I should put them all like this, shouldn't I? All like that. So it's all, everything in there, carbon dioxide, everything in there is nitrogen. Okay, and this one was going to be S bar naught at 2 minus S bar naught 1 minus R bar natural log. I'm just going to put 3 because we know the ratio of the pressures is 3. And then this one is S bar naught 2 minus S bar naught 1 minus R bar natural log of 3. Hopefully that all makes sense. I think I need another parenthesis. Yeah, these too many parentheses. Close this one, square. Close this one, square. I think that's right on the parentheses now. Okay, well, remind me, this we did look up at 300 Kelvin, and this one we looked up at 440 Kelvin. That was T2 actual. But now I want to find T2S. So isn't this now equal to 0? And this is at T2S. That subscript on that bothers me. 2S on S, whatever. But I think you get the idea. This is evaluated at T2S. T2S. That's the unknown temperature. What's your strategy? Is these nasty words. Guess and in the tables, Professor? Hey, you should do this at least once a month in thermo, right? Guess and iterate in the tables. It's painful, isn't it? Have you done it? If not, hey, let's repeat this class next semester. We'll have fun again. No, come on, you should do this. And you know what? Computer codes do this all the time. So it's not like I'm asking you to do something tricky or incredibly stupid. It's actually, if you actually code the computer codes, that's often what they're doing anyway, is they're guessing and iterating. Go back and look at numerical methods about the secant method or Newton-Raphson method or bisection. You know, they bracket it. They need to get close. Otherwise, if it's nonlinear, they can diverge and go off the crap, you know, get garbage. But anyway, guess and iterate. So you just start playing. And so after a little bit of this and this, you can get that you find the final temperature. And the final temperature, T2S is? T2S comes in around 402 Kelvin. Okay. Then you get this enthalpies at 402. Now you can calculate the reversible work. Reversible work, then you take the ratio, you find the, that's a typo. It's about 72 point something, 72.5-ish, in that vicinity, okay? 72.5%. What is this? This is wrong too. What is all this wrong stuff? Sorry about that. Guess what we do? We solve the same problem again, but guess what is changed? What happens when they give you this information right here? You use the approach of constant specific heats with these values given. So, since we're familiar with the problem, how does it change our equation for the power for that compressor? Let's say that we still were able to calculate the molar flow rate of the nitrogen. We want to get that change in the enthalpy of the nitrogen, right? The H2 minus H1 of the nitrogen. And then we had the molar flow rate. This is bar. Molar flow rate. And then you had H bar 2 minus H bar 1 of the carbon dioxide, CO2. How would you change? Well, you'd replace this by C sub P, T2 minus T1. And if you stayed with the molar flow rates, you need the C sub P bar. And then the C sub P bar, T2 minus T1. This would be of the nitrogen. This would be of the carbon dioxide. Did they give me C sub P or C sub P bar? What did they give me? Which one? Okay, so I want to get C sub P bar. I'm given C sub P. I think they're equal, and I'll just ignore the units. I think I need to multiply by the molar mass. I think I need to divide by the molar mass. Which one is correct? They give me C sub P in the table, but I really want C sub P bar. Well, you just check your units. It's kilojoules per kilogram Kelvin. I want it kilojoules per kilomole, so I multiply by kilograms per kilomole, and that was big M. I multiplied by molar mass. Make sense? Okay. So that's how you would solve for part A, and even how to get the molar properties. Or you can just use get the mass flow rates. We had that too. Okay. How about for part B, the rate of exergy destruction? Well, it was all down the sigma, and it was, I'm going to put it in a mass flow rate basis. It doesn't really matter, does it? Mass flow rate of the nitrogen, and then we had C sub P of the nitrogen, natural log of T2 over T1 minus R natural log of 3. I'm going to shortcut that one. P2 over P1, fine. P2 over P1. Close bracket nitrogen plus the mass flow rate of the carbon dioxide times the C sub P of the carbon dioxide, natural log T2 over T1 minus R, natural log of P2 over P1, just close it in carbon dioxide. So think about it. This term, you already had to have it for the part A. Same here. What about this? Is this R bar? Is this 8.314? No. It's R divided by the molar mass, isn't it? So maybe you put the molar mass of nitrogen and put R bar there. R bar divided by the molar mass of carbon dioxide. And then we already worked out these pressure ratios are 3. The pressure ratios are 3. And the T2 is given. We calculate sigma dot. And then you calculate exergy destruction. All right. Part C. Isentropic compressor efficiency. Didn't we just take this equation, modify it, say 0 is equal to, and now we do the m dot nitrogen, and now we have C sub P natural log, I'm going to call T2S divided by T1, that's what we need to find, T2S, minus R natural log, I'm going to shortcut that to 3, plus the mass flow rate of carbon dioxide, C sub P of the carbon dioxide natural log of T2S divided by T1 minus R natural log of 3. All right, I'm trying to go a little faster, but does that make sense? So you're trying to find this temperature right here, T2S. I'm always amazed at how students actually solve an equation like this on an exam. So I asked this at the 8:30 class. I said, how many people would kind of code that up and leave that as an X and then use the equation solver in their calculator? I see a few people already. Yeah, that's pretty smart, right? True? If you don't know what they're talking about, find a friend and have them show you, because I think at this point it would be advantageous to code it up on a time-limited exam and then use the calculator to its full capability.
Could you use the T2 over T1 equals T2 over T1 is to find your TS?
Absolutely. Now, what he's getting to is going to take too long to derive, but somebody says, isn't this deja vu? T2S divided by T1 is equal to P2 over P1 to the K minus 1 over K? Ideal gas, constant S, constant K, yeah. Your K is not 1.4 though. K of the mixture is the C sub P of the mixture divided by C sub V of the mixture. How do you get C sub P of the mixture? It'll be the sum of the mass fractions times CPIs. How do you get the C sub V of the mixture? The sum of the mass fractions times CVI. Oh, you could work it also on a molar basis too. Then this would be CP bar divided by CV bar. And then what is CP bar? CP bar would be the sum of the YI's CP bar I. It's all on a molar basis. And likewise, CV bar, blah, blah, blah. Yes, you'll get the same answer with some round-offs, but it'll be there. Okay. Final temperature is very close to the one using the tables. It's like 402. Temperature T2S is like 402. And the isentropic efficiency is around 72.5%. The answers are all very comparable because I tried to pick the average C sub P and C sub V values in the temperature range of interest. All right. Any comments on that?